Thank you, Mauricio, and thank you all for being here today, for joining us. We will discuss today, we will review today some general concepts on rifting and some examples from Argentinian basins or other basins around the world. This is the agenda for our presentation today. We will first start by looking at the East African Rift, and which is a present-day example of rifting. Then we will continue reviewing some concepts on rifting and tectonostratigraphy that will be useful for the pursuit of the talk. We will see some examples of rift characterization, and but in particular, an example of rift evolution to passive margin, and the example of the Mesozoic rifting evolution in the South Atlantic realm, particularly offshore Argentina. We will then take a look at the sedimentary evolution of rift basins with some examples of continental and marine settings for rifting. Then we will look at some exploration examples in rift basins and passive margins, both in Argentina and some others from around the world. So let's start by the East African Rift. If you see these features here in the center of the, let me put the pointer, just 1 second. If you see these features here in the central part of the screen, you will see these elongated features from bottom to top that are oriented, let's say, from bottom to top. This is Eastern Africa, so it's from south to north and then turning towards the northeast. You see that there are some lakes associated with this system, and particularly note the elongated features, and this system joins the Red Sea and the Gulf of Corinth in northeastern Africa. This is the East African Rift. You see that it has 3 branches. In particular, here you will see the 2 branches splitting between Uganda and Mozambique, Tanzania. And this system is active in the present, and it initiated in the Miocene around 25 million years ago. It's formed of a series of narrow, roughly north-south oriented, elongated fault-bounded basins. And it's characterized by crustal extension in the east-west direction, or approximately east-west, negative Bouguer anomalies, thin crust and lithosphere, and a high surface heat flow and volcanic activity. And to represent this volcanic activity, one of the many volcanoes, but probably the most well-known volcano in this part of the world is the Kilimanjaro Mount. Thermal anomalies produce uplift in the reef shoulders, and uplift can also be produced by doming produced by these thermal anomalies. It's important to notice, for example, this is a section, an east-west topographic section across the rift in the northernmost part. Here is marked by the red line on the map. And you will see that these features, they are extensive. They generate troughs, so low areas where sedimentation occurs, but they also generate highlands that are submitted to erosion and provide the sediments that will deposit in the rift valleys. These highlands can be uplifted by regional uplift due to doming, or local tectonic uplift due in the footwall of the basin forming faults. This is a GPS velocities map for Eastern Africa, and you can notice the difference in the velocities measured in Somalia, here to the east, compared to the central part of the graben, or the western part of the graben, which moves at a slower at velocity. This is the consequence of this differential movements, absolute differential movements, is extension along the eastern branch of the East African Rift. So present day, there's extension here, there's volcanism, and because the Somalian plate is moving to the east or to the southeast faster than the central part of Africa. Okay, if we want to review some general concepts on rifting, let's, in a nutshell, there are two end members of rifting mechanisms, which are called active rifting or passive rifting. In the case of the difference between the two is the origin of the uplift of the asthenosphere. In the case of active rifting, the asthenosphere is actively pushing up and moving up, and this produces doming. So there's a thermal anomaly that's making the isotherms go up, and this is producing extension and volcanism here in the surface. If we look at passive rifting, the difference here is that it's not that the asthenosphere is actively moving up, but it's the far field stresses that are pulling apart the lithosphere, and so the asthenosphere is passively moving up. The consequence is the same. The asthenosphere moves up, the heat flow is increased. The difference is that in this case, there's a thermal anomaly that's pushing up, and the asthenosphere is actively moving, going up, while in the case of passive margin, it's passively moving up, produced by the extension that's occurring due to far field stresses that are actually, in most cases, related to subduction. Subduction produces horizontal stresses, both that can be either compression or extension. So what does the thermal evolution of these basins look like? If this is the initial state with a 1300 degrees Celsius isotherm marking the top of the asthenospheric mantle, during rifting, there's the 1300 degrees Celsius isotherm is going up. So there's heating, there's increased heat flow here at the surface. And then during the cooling stage, and this is after rifting in the sag phase, the isotherm of 1300 degrees Celsius is going down, everything is cooling and it's sinking. So this is producing the thermal subsidence that's common in the post-rift stage evolution of rift basins. How does rifting can produce continental breakup? We are all familiar with the Wegener theories that and the hypothesis of the split of Pangaea in different continents, that of which these coastlines seem to match perfectly, like the pieces of a puzzle. It's due to rifting that these continents can break apart. In this map of Pangaea, here for the Triassic or the end of Permian, you see in colors, well, you see obviously the different cratons and tectonic blocks, the Paleozoic and Precambrian orogens that amalgamated all these cratons in a supercontinent, and also the terrains that were accreted to the southwestern margin of Gondwana and Pangaea throughout the Paleozoic. What's highlighted here in colors is the Triassic breakup of Laurentia from Gondwana in the Triassic. Then in blue is highlighted the Jurassic breakup produced during the Karoo rifting in the early Jurassic. and continue through the mid-Jurassic. And in green is marked the Cretaceous breakup. In particular, note this breakup between South America and Africa that produced the opening of the South Atlantic Ocean, but also that the Cretaceous breakup locations that produce the separation of the different blocks of Eastern Gondwana throughout the Cretaceous and Cenozoic. If we think which of those rift modes and mechanisms and what can be the origin of those for breaking the continents, we get that 3 processes can be responsible for continental breakup. We were before talking about a thermal anomaly that produces the active uplift of the asthenosphere. An example of this is the Karoo mantle plume that impinged here in Eastern Africa in the early Jurassic and produced rifting, volcanism, doming in this area, and split it eastern from Western Gondwana in the early to mid-Jurassic. Another process that can produce rifting and continental breakup is orogenic gravitational collapse. This requires the build of a collisional orogen, and then when submitted to extension, it can split up and produce rifting. And finally, all the subduction related processes that can produce extension in the retroarc, in particular associated with slab retreat, negative rollover, or slab steepening. We are always talking here about the behavior of the subducting plate, which we call slab, below the supercontinent. So this can produce either extension in the retroarc, in the proximal retroarc, or as far as 1,000 kilometers, depending on the depth of the mantle convective cell. For example, there are some recent hypotheses that suggest that the South Atlantic could have been produced by subduction-related extension in a very far position associated to the location of the trench and the South Atlantic breakup location. And this is an example of this passive upwelling of the asthenosphere in passive rifting, as could be the example of the South Atlantic. Okay, let's talk a little bit about some general concepts of rifting. You know that rift basins are fault-bounded basins that are submitted to extension, and where the hanging wall subsides and creates accommodation where sediments can be deposited. The basins can have a half-graben shape. So this is a basin that's flanked by one fault-bounded border, which is, for example, this case, and the other one is what we call a flexural border, and it's an asymmetric basin. Symmetric rifts are what we call grabens, and they are both bounded by 2 sets of antithetic normal faults that produce a trough in the middle, and this is a graben. And also rifts can be distributed along they can be narrow or wide in terms of the area, the width of the area that's submitted to extension, and it can also be, in this case, show distributed. One single half graben, as we said, a fault-bounded border, which is in this case is here. This is a plan view, so from the top. And it has a approximate arcuate shape like this. And if we see in a 2D section, in a vertical 2D section, we have this faulted boundary and the flexural boundary on the other side. Obviously, the sedimentation will be controlled by this geometry. And if we see a section across, it will look like a saw with overlap on both sides. You need to be perpendicular to the fault or oblique, but cutting the fault to see the wedge shape. How do these rifts evolve? How do they evolve? They evolve in different stages. First, there's rift initiation with the nucleation of isolated small faults, which in the next step start to link, and they produce larger deposenters. And in a mature stage, the formation, the strain is localized along these fewer but larger faults. Okay, so that was about the geometry of gravens. Let's now talk a little bit about the concepts of tectonostratigraphy. So we know that these rift basins are formed by tectonic stresses, in this case, extensional tectonic stresses that produce the opening of rift basins. In terms of the stratigraphy of the strata that can be found in rift basins, we can classify them in these three large groups, starting by the pre-rift, which is all the strata deposited before the onset of rifting. These strata tend to be parallel and to be truncated by an erosive unconformity that, in the case of rifting, we call the rift onset unconformity, which is the base of the sediments that will be deposited during the rifting. The pre-rift sediments normally are, we said, they are parallelly bedded, or they can be part of a previous event. They can also be seen rift, but from an older event, and they are deformed, and usually they can be rotated and truncated, forming this kind of geometries. Seen rift, the strata deposits during rifting, so during the the moments of activity of normal faults, which produce extension and normally rotation of tilted blocks. Seen rift strata tends to show the growth of these faults, presenting a fan shape, wedged, and finishing in onlap with both flanks, but in particular they present a wedge shape against the faulted boundary of the half graben. And this is, for example, we can have different seen rift events recorded in a single deposenter. For example, in this case, seen rift 1, seen rift 2, seen rift 3, seen rift 4. Different seen rift events associated to tectonic pulses of extension and fault reactivation throughout the rifting process. Finally, once rifting has stopped, active extension has stopped, we saw before that when we stop extension, the system cools down, and this cooling produces subsidence, but in this case, not fault bounded, but subsidence more largely distributed. Normally, sediments of the post-rift tend to unlap the basin borders outside of the half grabens or the grabens, and here we need to differentiate two end cases. If the rifting is aborted, this meaning it's not successful, we get this post-rift wedge, which is what we call the horns of the rift, with this geometry with unlap against the basin flanks. And if rifting is successful, so rifting extension succeeds and produces the opening of an oceanic basin, in that case, we get the formation of this breakup unconformity at the top of the seen rift and the base of the post-rift, and we start, and we have this passive margin prism, that's what we call the drift. So the drift is also produced by thermal subsidence, but it's in the case of successful rifting. Let's see some examples of pre-rift, sin-rift, and post-rift. And these examples are coming from the Colorado Basin, offshore Argentina. Here we see two 2D sections across the Colorado. This is the north-south one. So to the left is the south. Is here showing the Colorado Basin. We see it's half graben. We see there are some tilted blocks on the northern flank, such as that one. And these tilted blocks are formed by pre-rift strata. In this case, these are Paleozoic strata in the pre-rift that was deposited before rifting and was deformed and was part of these tilted blocks that formed during rifting. So the strata is pre-rift, but the tilted blocks form during rifting. This section goes north and is showing the southern part of the Salado Basin. We see here in the Colorado Basin, this is the west-east section, and it's showing different sin rift wedges. You see the sin rift are these wedge, triangular shaped wedges of sediment that are fault bounded. In red, in blue are highlighted different groups of faults. And in this work, we have interpreted 3 different generations of faults, the red faults being the oldest faults, and then transected by the blue faults, which are responsible for the formation of the main deposenters of the Colorado Basin, such as the central or eastern deposenter. And finally, here to the east, we have interpreted these faults in green, which are oriented parallel to the continental oceanic boundary. They are forming producing these half grabens on the external part of the continental domain, and are associated with the SDRs, which are some volcanic wedges that form during breakup that we will see just in a minute. So these green faults are the 3rd group of faults that we interpret that developed during the early Cretaceous, during the rifting and breakup of the South Atlantic Ocean here in the Argentinian offshore. Okay, we said that successful rifting produces the opening of an ocean, and oceans are bounded on each conjugate margin by passive margins. Passive margins can be of 3 archetypes or 3 end members. Type A is magma poor, so a hyperextended lithosphere, continental crust, and sometimes you can have exhumed mantle. This is, for example, the Iberian-Newfoundland margin here in the Central Atlantic. Another end member is the case of the transform margins here, as here in the equatorial Atlantic, in the equatorial segment of the South Atlantic, actually, as in the Ghana platform. These are abrupt margins produced in these areas of strike slip displacement between the continents. So these are abrupt margins, and they are developed both on the African, as in this case in the equatorial Atlantic, developed both on the African and on the Suriname, Guyana margin in northern South America. And finally, the example marked here in C is a volcanic margin or a magma-rich margin, which is characterized by the emplacement of these SDRs. SDRs stands for seaward dipping reflectors. It's a series of reflectors that were identified on seismic data that dip towards the ocean. This is why these are seaward dipping reflectors. And at the beginning, they didn't know what they were. Then they were drilled, and we found out that they are successions of tholeiitic basalts with aeolian or shallow marine sediments, and they are interpreted to form during the process of breakup in these magma-rich or volcanic margins. These SDRs are developed on the continent-oceanic transition zone. This is the COT, continent-ocean transition. They are, if we see this model of emplacement by McDermott, we can differentiate between the inner SDRs that are fault bounded. They are normally limited by faults deeping towards the continent, and we can differentiate them from the outer SDRs or external SDRs, which show kind of merge of the seaward end of the wedges towards the magmatic crust of the future oceanic crust in this transition zone. These are interpreted the SDRs are interpreted to develop during the breakup process, so they record a gradient between more brittle rheologies associated to rifting for the older SDRs preserved in the inner part of the continental crust of the continental ocean transition zone, while they show this gradient towards more ductile conditions, rheologic conditions, which is the case of these outer SDRs or external SDRs that seem to merge with the magmatic crust, and they form until the first normal oceanic crust is produced, as in this case here at the bottom, in subaqueous conditions. So for the rest of the SDRs, they are normally formed in subaerial or very, very shallow marine conditions, while normal oceanic crust develops at a determined water depth that's necessary to produce normal oceanic crust with all these, columnar basalts, pillow lavas, etc. Okay, let's take a look at some examples of rifts. Another example, this is the Malvinas Basin in southern Argentina, offshore southern Argentina. We see here two half gravens bounded by faults that are dipping towards the west. This, I'm sorry, here is not marked. The left is the west. You see the location of this section here at the bottom, and you see the seam rift, and then you see the sag phase. And then, okay, we can characterize these rift basins on seismic, and then we want to assign ages to these rifts. So if these rift basins are cropping out, you can get data either from, obviously from rock samples, but you can date either volcanic rocks, you can get fossils that can get like paleofloras or nano or micropaleontology fossils like forams or other kind of microfossils that can be used to assign an age to strata. And another method you can use is detrital zircons. So the detrital zircons require active or recent volcanic activity during or prior to the deposition of the source of the rocks that are preserved within the gravens, within the deposenters. So we carried out the detrital zircon chronology here in the Malvinas Basin. We obtained rock samples from two wells at the bottom. Also the total depth of the well, we recovered in this Arizo well, we recovered a volcanic breccia. This is the thin section. This is what the thin section looks like. There are clasts of tuff. This is what the core looks like. Okay, it's a volcanic breccia. And these are the microscopic photos of the zircons that were recovered from this rock. This is an histogram showing the age distribution of these ages of zircons. From a total of 149 zircons, we obtained some inherited ages of 296 million years and some ages in 215, which we interpreted as the deposition age of this rock. The ages of the zircons that you can recover in this method can be the zircons can form at the same time of the position of the rock or before. So this is why we could get ages of all the provenance areas for that rock in that location, and we interpret the youngest age as the maximum depositional age In this case, because it's volcanic and it's very proximal, we interpreted a crystallization age of 215 million years ago, which is a late Triassic for the Malvinas Basin. And you can see here at the seismic line that that sample was recovered from the bottom of that well here in the bottom section of the well here in the pre-rift, in the early rift. You see the purple is the top of the pre-rift. The rock was recovered from above that in the seam rift section, and it provided a late Triassic age. Another sample was recovered from the Calamar well. In this case, we took a sample from the top of the seam rift, which is called, the main seam rift is called the Tobifera series. We confirmed the middle Jurassic age for the Tobifera series as part of the Jonaica magmatic province. Here you see that the Tobifera, which is this white tuffs and ignimbrite. In this case is a tuff. And you see the unconformity and the position of the Spring Hill Formation on top of that. This is what the very prismatic elongated circumcrystals look like. And they provided a single peak of 169 million years for, so this is Bathonian, for the deposition or the crystallization of this Tobifera series at the top of the seam rift in the position of the Calamar well, which is located here to the west of the Malvinas Basin in the Rio Chico High. So we compiled the ages for the rifting in the Malvinas Basin, and we differentiated two rifting events, one in the Triassic, which was the sample recovered from the volcanic breccia, and another rifting event. So this was the first time that the Triassic rifting was identified in this area, in this basin. And then we confirmed the middle Jurassic age of the Serie Tobifera in the Malvinas Basin as part of the large Jonaica magmatic province developed in the Jurassic here in the southwestern Gondwana. Okay, let's now take a look at the complex rifting histories. This is some examples. Complex rifting is it can be very complex, and there can be several rifting events cross-cutting each other that could eventually produce an oceanic basin or not. For example, this is the case of East Africa, and you see that there are Carboniferous to Triassic rifts, Jurassic rifts in blue, there are Cretaceous rifts, and finally there are Miocene rifts that's active in present day. And another case of multi-stage rifting is the North Atlantic between Greenland and Norway. In the South Atlantic, we have compiled the ages of rifting in different basins in Southeast and South America. So we put with the bars the age of active rifting for Triassic, Jurassic, and Cretaceous basin for all these basins. And I'd like to highlight here that this orange polygon is representing the part that's submitted to the Andean compression and orogeny in the Cenozoic. For Africa, we did the same thing. We compiled the ages of rifting of all the Mesozoic rift basins that we could identify in the southern part of Africa, especially the southwestern part of Africa. And what we did was to put these rifting ages in black, and then we have in gray the ages of post-rift or not active rifting. We wanted to understand how did Southwest Gondwana broke apart and produce the South Atlantic Ocean. This is a pre-rift configuration, and this is very important to highlight here the inheritance of the basement. Here we see all the cratonic blocks, the cratons and the orogens that were responsible for the amalgamation of these cratons and formation of the supercontinent. We also see tectonic plots that were accreted to the southwestern margin of Gondwana produced by subduction and accretion throughout the Paleozoic, and finally the Patagonia terrain here to the south. This Patagonia terrain accreted in the Permian and produced a fold and thrust belt that can be followed between the Ventania system in Buenos Aires, across the Colorado Basin, and in the Cape Fold and Thrust Belt in South Africa. So we wanted to see how did the Mesozoic rifting occurred. We identified for the Triassic 3 groups of extensional basins. In number 1 is all these basins associated with retroarc extension. In the Triassic, there is an absolute movement of Gondwana towards the northeast. And so all the area here is abducted to retroarc extension. We have the formation of the Cuyana and Neuquén basins, an extension, and the epicenter here in the Malvinas basin of the sample that we just saw. Also, this extension produces intracontinental rifts here in Central Africa, extending into Brazil, and the extensional reactivation of the fold and thrust belt produced by the collision of Patagonia, that in the Triassic is, at least in the late Triassic, is extensionally reactivated and forms the epicenters. This is a section between the Andes, showing active subduction with a volcanic arc, retroarc basins, extensional basins. In this case, the Cuyana basin occurring over the suture between two Paleozoic terrains. In the Jurassic, there is the impingement of the Karoo mantle plume in Eastern Africa that produced a split between Eastern and Western Gondwana. And there is also the development of the Chonaike magmatic province, here shown in pink, producing volcanics in all this southern Patagonia area, and even in northern Patagonia. There's a diachron, it's diachronous, the magmatic province is diachronous from north to south. The younger rocks are deposited here towards the southwest, and in the Rocas Verdes oceanic back-arc basin. And we see here the development of the Jurassic rifting in the Malvinas associated with the Tobifera formation. As we can see here, these models here in C represents the rifting and the magmatic and the troughs deposited as part of the Tobifera series in the early to mid-Jurassic in the Austral and Malvinas basins. In the late Jurassic, so extension continues. We have here these late Jurassic rocks of El Quemado, associated with bimodal rifting that will then produce the opening of this back arc Rocas Verdes basin towards the west and southwest of the Austral basin. And in a far distal position, we have rifting along the Rawson Valdez, North Malvinas basins, and in the Oteniqua basin here in South Africa. This rifting is going to be oblique to what's going to be the continent-ocean boundary between South America and Africa, which will go across this in an oblique way across this rift system. And we compare this with the oblique rifting that occurred in the Gulf of Aden in the Cenozoic. We have a similar configuration of this 90 degrees elbow between the Red Sea and the Gulf of Aden. In this case, is the future reach of the Mid-Atlantic and the Agulhas Malvinas fracture zone between Africa and the Malvinas Plateau. For the early Cretaceous, we have the opening of the southernmost segment of the South Atlantic here, north of the Agulhas Malvinas fracture zone, and in placement of SDRs towards the north. These SDRs, these magmatic wedges of basalts and shallow marine and aeolian sediments that are formed during the breakup. And this is the evolution for this part of the South Atlantic. Finally, a representation for the Aptian, with oceanic crust already being accreted here in the central part of the Atlantic, and subsidence on top of the SDRs. The Aptian is the moment of transgression of the ocean, of the sea, or above the coastlines and the position of source rock. Okay, so I don't wanna, let's move forward to the sedimentary evolution of rifts. Here's an example of a rift system in Africa. And rifts can be filled with either continental sediments, marine sediments, or both, depending on the proximity to the sea. In the case of continental environments, the sedimentary environments that can develop depend on the climate conditions, depend on many factors, but particularly the climate conditions. In arid climates, we have development of alluvial fans at the bottom of the fault bounded on the fault boundaries of the half-gravens. We can have some fluvial systems. We can have some deltas if we have some enough hydric balance to create. If it rains enough and it's not evaporated enough, and we can preserve some water bodies like lakes. We have lakes. We can have deltas. If we have deltas, we can have coal seams in the deltas. The deltas supply sediment towards the lake, and this can produce turbidites that can reach the deep water part of the lake. And what's particular about these rifts filled with continental environments is that you will not find marine fossils. You can find plants, you can find dinosaurs, you can find any kind of continental animals, but not marine fossils. This is one of the key elements to differentiate from marine environments, right? Let's see some evolution of these rifts filled with continental or developed in continental environments. This is a very nice evolution set from Gothorpe and Leader 2000. We see that in the rift initiation phase, we have isolated deposenters bounded by faults with not a lot of relief between them. This system evolves to this B, which is the fault linkage stage. The faults start to connect. They are linked, and so the deposenters become larger, and some other fault segments can become inactive. It's important here is that the faults can be connected, creating larger deposenters. We have erosion in the footwalls that are the catchment areas for the routing systems that produce this kind of deltas or alluvial fans or fan deltas, depending on if we have a lake or more like a playa lake, depending on the hydric balance. Not all the segments are going to be the same. Some have gravens, some deposenters can have development of lake systems, and others may not. It depends on the water balance. And in the case of deep lakes, you can have turbidites. If we go through the next section here in the C, marked by C, the continued growth, here we see that there is less local relief, and there's the development of these axial fluvial systems that connect different deposenters and interact. They are asymmetrical, and they interact with the footwall fans here towards the fault-bounded border of the half-gravens. And in the final stage, you can have inactivity of the fault, and maybe sometimes displacement of the active faults towards the deposenter. Let's see some examples of continental rifts. This case is from Argentina, and we have the development of a rift basin here. You see the active fault. Here you have the uninterpreted and the interpreted section. You have the active fault. That's and these are the footwall alluvial fans or fan deltas, depending on the kind of environment that they reach. This can be getting into a lake, so there could be some lacustrine source rocks associated to developing in that lake. And so the lacustrine shales can be the source rock, and the sandstones deposited, the sands deposited in the fan deltas or the alluvial fans can be the reservoirs. This is what shown with the drop of oil. And there can also be some carbonate phases, as in this example here from Patagonia, where you have an active fault with alluvial fan or fan delta deposition, and you have some bioermal phases belt here along the fractural border of the basin. Another example of lacustrine seam rift or rift basins filled with the continental rocks is the central Atlantic. The central segment of the South Atlantic. In this case, the Brazil, West Africa margin. This is between Brazil and Central and Angola, Congo, when they were still united in the early Cretaceous. The rift basin developed with these brackish lacustrine systems. And these are two 3D models that show very nicely the deposition of the lacustrine shales in the seam rift and of carbonates on the structural highs in a lake, in an hypersaline lake. This is the pre-salt of the central South Atlantic. Then there's a bed of salt above this, and then after breakup, the passive margins develop. So this very, very prolific source rock can be up to 25% TOC, is what's known as the Bucomasi in Angola or the Lagoa Feia in Brazil. It's very prolific, and it's the prolific source rock feeding all the oil accumulations in the pre-salt of Brazil and Angola that have been developed in the last decades. In the case of marine flooded rifts, here let me show you some key elements. Here the flooding depends on the sea level, so they can be, during the high transgressive system tracks and high stands, basins can be flooded, and then they can become subaerially exposed during low stands. The systems that the sedimentary environments that can develop are the same, fan deltas and also other kind of deltas with development of coal seams. And there can also be some carbonates associated to the marine floodings, especially in areas with less sedimentary input, because remember that we know that carbonates need clear waters to develop. And some tidal deposits or subcas can develop in arid climates in this kind of flooded rift basins, marine flooded rift basins. Diagnostic for the determination of marine environments is the presence of marine fossils or microfossils, and the source rocks can be type 2 or type 3 in more deltaic environments. Okay, this is an example on how the basins can be flooded during the transgressions, and they can be subaerially exposed with development of more fluvial or continental environments during low stands. Okay, so before we finish, let's see some examples of rift basin related plays explored in Argentina and the world. This is an example from Malaysia, where they produce hydrocarbons from fractured basement charged of oil that's generated in the seam rift hosting source rocks, lacustrine source rocks in the seam rift. The oil is generated and migrates to the reservoir, which is a fractured basement. This is in a case of a structure like a horst. And you can also have structures that are tectonically inverted by compression, as in the case of the Winkle Ridge in the Neuquén Basin in central western Argentina, where you have source rock in the seam rift or the post rift, and this oil migrates towards the structural highs, which in this case are basement pop-ups with uplifted, and it creates fractured basement can develop reservoir conditions and thus produce hydrocarbon from the compressive structure. Another example of oil produced in rift basins is in this present day Eastern Africa Reef system. This is showing the chronostratigraphic charts. You see the ages here for different lake systems here in the western branch and in the eastern branch of the south of the Eastern African rift. You can see that not all of some of the rifts have lakes. This is shown here in the Miocene and Pleistocene section with these brown rocks are the lacustrine shales that are actually source rocks, so they are deposited under anoxic conditions and they preserve the organic matter and they have kerogen that can produce oil. And there are also some sandstones and reservoirs associated to those and the flanks of those basins. And for example, compared to what's happening in the western branch of the East Africa Rift, towards the east, you have development of much more volcanic and volcaniclastic phases and less source rock development. So obviously the western branch is much more favorable for development of petroleum systems than the eastern one. And actually, I'm going to show you now an example from the Lake Albert here in Uganda. And this was to show that not necessarily all the deposit centers have the same infill, even if they develop at the same age. One can be filled with a lake or deep lake, while the other one can be filled with volcanics or volcanic rocks or shallow lake environments, such as in this example. So I was saying the example from Lake Albert in Uganda. This, if you see here in 2006, there have been some oil spills, I mean, some outcrops of oil, natural outcrops of oil, described here since the 30s. And in 2006, they drilled this well, Kingfisher, that found Miocene to Pliocene sands that flowed 14,000 barrels of oil per day of oil with little CO2. Some problem that they have here is because they have a lot of volcanic activity around that they can have CO2 in the reservoirs, but in this case they found the right spot with very good hydrocarbon flow. It's mostly heavy oil, but then in a few years they made more than 20 discoveries in the Lake Albert area. You can see here some of these discoveries shown in green and in yellow and in red. And an example of this extensional normal fault and the reservoirs developing and the trap being fault bounded, so it's a three-way deep closure against fault. And this is what the reservoirs look like. Okay, so let's now see some examples from Argentina. Here we see all the Mesozoic, all the sedimentary basins of Argentina, and in orange are highlighted the hydrocarbon producing basins. So from the 6 hydrocarbon producing basins, 5 of them are associated to rifting. The Paleozoic basin is not associated to rifting, but all the other 5 basins are. We will see first an example from the Triassic Guyana basin. Here we have a seam rift system a rifting system that developed on the suture between the 2 Paleozoic terrains. There are 2 branches of deposit centers. The productive one is this one here in Mendoza area, and there's a seam rift with red beds that have all these units have reservoirs, and the source rock is here deposited in the late seam rift or early sag, which is called the Cacheuta formation. It's a lacustrine source rock of type 1 kerogen and TOC from 3 to 10%. What's particular about the Guyana basin and also of all the other the Subandean basins in Argentina is that they were submitted to compression during the Tertiary. So in the case of the Guyana basin, this compression produced deposit center inversion, tectonic inversion, and this tectonic inversion is responsible for the generation of traps. What's important from the Andean orogeny also is the deposition of foreland sequences that usually help maturate the source rocks. So the overburden of the Cenozoic assists for maturating the source rocks. Now we will see some examples from the Neuquén Basin. We already saw one of the fracture basement. Now, the Neuquén Basin is a very prolific basin with several source rocks deposited in different environments. We will focus in the Sin Rift sequences here at the bottom, which is what we call the Precuyo or Precuyano cycle, responsible for rifting and the formation of half gravens that can be filled either with volcanics or with lacustrine sediments. For example, here in the Neuquén Basin, we have an example of a half graben. This structure here formed by this fault would be this one. There is some inversion which produces accumulation of oil generated in the lacustrine source rock in the bottom of the Precuyo, and this oil migrates and can be accumulated either in the volcaniclastic phases of the Precuyo, as in the case of the Loma Negra field, or in the Cuyo group above in the early to mid Jurassic. In the post-rift, the oil can also migrate, but the inversion of these older normal faults, tectonic inversion, creates structures that assist the accumulation of hydrocarbons. Another example from Patagonia, this is the San Jorge Gulf Basin. This is there are Jurassic and Neocomian rifting. There are two source rocks identified here, one in the Neocomian, which is in Rift, and one in the D129, which is in the SAG. In this case, this is Neocomian, early Jurassic. The D129 is the Aptian. And these are both lacustrine source rocks that produce mostly oil, and this oil can be trapped in tilted blocks or three-way deep closures against faults. There are many normal faults on both flanks of the basin, and the accumulations are distributed here on the flanks of the San Jorge Gulf Basin. This is a maturity map showing the gas and oil window for the source rocks. And another particular thing is that the western part is submitted to compression of the Andes in the Cenozoic, and there's a development of a fold and thrust belt, which also creates the compressional structures and thus structural traps. Okay, let's see an example from offshore. This is the Colorado Basin. In the Colorado Basin, we have several plays, either in the Sin Rift, which can be these alluvial fans and fan deltas associated with lacustrine source rocks in the deposenters. And after the breakup and the South Atlantic breakup, we have the marine transgression in the Aptian, and we can also have accumulations in structural closures, in carbonates, self-contained carbonates, let's say stratigraphic traps, or stratigraphic traps associated with turbidites in the passive margin. Okay, let me just close with this because it's already the time. Some final remarks on this talk. Rifting is an effective mechanism for basin formation, creates conditions for development of numerous petroleum system elements, particularly source rocks. Petroleum systems cannot exist without source rocks, but also reservoirs and traps. Rifting can be complex. Successful rifting leads to passive margin formation, such is the case of the South Atlantic realm that we saw its evolution before. Rift basins can be filled with continental or marine sediments, and in both cases you can have lacustrine, marine, or deltaic environments that are useful for the deposition of source rocks. and reservoirs can be present in either in the pre-rift, the syn-rift, or the post-rift. And tectonic inversions, as in the case of the Andean foothills, can create structural traps and add overburden to maturate syn-rift source rocks. Thank you very much for your attention. Now, if you have any questions, I'm happy to answer.
Okay, thank you very much, Juan Pablo. Excellent presentation. So from this moment, we will start with the questions and answers round. This will last approximately 30 minutes, and during this time, you can continue sending your doubts. Initially, we will select one question per participant, and in case of have time left, we will include more questions for those who have asked before. Okay, Juan Pablo, we have 3 questions. The first one is, how can Insights Valley deposits reflect an influence from syn-rift tectonism?
I'm sorry, can you repeat?
How can Insights Valley deposits reflect an influence from syn-rift tectonism?
Thank you. Okay, Insights Valleys can occur in two environments or in two settings. Let me show. Let me go back to the slide of the Insights Valleys. I was the requirement for syn-rift is that the faults are bounded by the sequences are bounded by active faults. So what you need to in order to interpret the tectonic evolution from the stratigraphy, so this is the tectono-stratigraphic evolution, it's necessary to determine, to see that the sediments are, or the wedges of sediment, or packages of sediment display the fanning architecture, and they are bounded by a fault. Incised valleys can occur either or incisions can occur either during rifting or also after rifting. If the basin is underfilled, the catchments can continue to be eroded, and the fluvial systems can incide and create incised valleys, even if they're not submitted to extension. The condition to interpret if that they are active rifting incisions is that they need to be bounded by active faults, and the activity of faults is interpreted from this fanning end towards the fanning onlap, let's say, and rotation towards the fault bounded border of the deposcenter.
Okay, Juan Pablo. The next question is there any preference for sediments coming from the boundary fault boundary or the hanging wall boundary?
It's a very good question. Obviously, both boundaries of the depositors are very different. What's interesting here towards the fault-bounded border of the basin is that the sedimentation is like in an alluvial fan or a fan delta. Sediments do not tend to be very well selected because the gradient is high here at the catchment. So the sediments tend to be a little bit chaotic. So the sedimentary classes, obviously the lithology of the sedimentary grains will depend on the lithology of the pre-rift that's being eroded here. It can be crystalline basement, it can be pre-rift. But the sedimentary grain size, the sedimentary classes, are not going to be well sorted. Normally, they will have a mixture of different sedimentary classes in these more chaotic deposits in the alluvial fans. However, you can have fluvial systems with better selection, and in particular, the deep water systems that can develop associated with these alluvial fans can be quite well selected. On the other hand, on the flexural side of the half gravens, you have less gradient, so you can have a better selection. And what's interesting about this side of the half gravens is that they are favored for migration of the oil that's generated in the lacustrine source rocks. The migration is, or marine, the migration pathways for the hydrocarbon that's being generated and expelled are favorable here in the flexural border. And these sediments can be more selective than the ones in the active, in the fault boundary. However, remember that these deep water systems that can develop either in lacustrine or marine conditions can be very good, display very good reservoir conditions, and they form stratigraphic traps because they are sandwiched between the lacustrine shales.
Okay, the next questions. In field, how can we know if we are in the expanding zone?
I'm sorry?
In field, how can we know if we are in the expanding zone?
In the expanding zone, what could
in
that
the
be?
rifting zone? Yes. Working in field.
In the field. Well, in the field, obviously, you have how you know you are in an extension, an area submitted to extension. You will have other examples of areas submitted to extension in the present day are, for example, the Basin and Range in the Western United States. You will have active faulting. This faulting is active. You will have high measurements of heat flow. You may or may not have volcanic activity, but in particular, you will have some elongated features on the surface that will reflect fault activity, and this will also be translated into earthquakes or the record of earthquakes that will show the movement or the displacement along these normal faults.
Okay, the next question. How big are the reef basins that have gravitational collapse as the dominant mechanism for rifting compared to those formed by active or passive rifting?
Okay, obviously we go back to one of the first slides. The Reefs basin associated with orogenic gravitational collapse, the size of these basins is associated with the size of the orogen, obviously, and but it doesn't necessarily happen all across the orogen. It can be localized along former structures. Yes, previous structures. In the case of active rifting, these mantle plumes normally cannot be larger than 2,000 kilometers in diameter. Let me check. I don't recall if it's diameter or radius. I think it's radius. So this comes from here. Now it's 2,000 kilometers in radius. This is, for example, the Karoo mantle plume in Eastern Africa. You see that from the center of eruption here in the Lebombo Limpopo triple junction, there are 2,000 kilometers of radius of activity for the volcanic activity, and this is also related to the size of the plume. Regarding the passive rifting associated with the South Atlantic and all the retroarc extension and the South Atlantic opening, I mentioned that there are some recent works that suggest that it can reach quite a long distance from the trench, this, for example, 2,000 kilometers, depending on the depth and the size of the convection cells of the mantle. If the subducting slab reaches stagnates in shallow depths, it creates only a very small cell, and extension can occur only quite close to the trench. But if the convection cell produced by the subducting slab reaches 1,000 or 2,000 kilometers in the mantle, it can produce extension and farther distances, and could be responsible for the opening of the South Atlantic at 1,500 to 2,000 kilometers away from the trench.
The next question. How do you distinguish the boundary between the synreef and post-reef units?
Yeah. What's important is that the synreef will be, let me show you this example. The synreef will be fault bounded, so the sequences can have this fan shape. You see that they split up, they finish against the fault, while post-rift, they passively unlap the shoulders of the rift. The basin, because faults, this is the synrift, and this is the post-rift in green. During the post-rift, faults are not active anymore, so the position occurs in larger areas, and there are these coastal unlaps on a wider basin produced by thermal subsidence, compared to the synrift, which is a more narrow basin with fault-bounded strata produced by active tectonism and active extension along these faults.
Okay, we have one more question. What is the magnitude of stratigraphic traps associated with reef system, and which is bigger, structural or stratigraphic traps associated with reef?
I'm not sure which of the two are bigger. There are examples of both. I think that in terms of the Subandian basins, because they are the ones that we showed here in Argentina, because they are all affected by the Andean orogeny in the Cenozoic, the development of structural traps is more important. And also structural traps are less risky, let's say. But in other settings, like in other settings of the South Atlantic, an example that I didn't show because of the time was this North Malvinas Basin. This is located offshore. I'm sorry, I will go back to the map. This is here in north of the Malvinas Islands, the North Malvinas Basin. Is a Neocomian rift system with development of an Aptian lake, similar to the San Jorge Gulf Basin, and also, and there some turbidites associated with the active faulted boundary of the deposenters have been identified, and you see that these turbidites are coming from fan deltas here at the footwall of the faults, and they are affected by this axial system because the basin is deeper towards the south, towards this area, and this is what the 3D model looks like. You have the footwall, you have the river systems, you have the alluvial fans, and turbidites associated to those deposited, embedded between the lacustrine shales of quite good, well-sorted sandstones that are trapped between the shales, so it's a stratigraphic trap, and it has been tested productive for oil in the South Atlantic. We also have examples of these lacustrine turbidites in the San Jorge Gulf Basin, and they can work. But I would say that for the subandean basins, the structural traps are more important and less risky, but are also the most obvious. So the most of them have already been explored. The challenge for the future is to find other kinds of traps in these prolific basins, and the stratigraphic traps are certainly they certainly have potential.
Okay, Juan Pablo, we don't have more questions. So again, thank you very much for the excellent talk. I'm sure that this was great value to all participants.